Okay, then allow me to get started. Good afternoon. A mix of things today. A little bit of partly sort of driven by how much demand you signal, going over some of the more subtle points from last week's lecture inside the parse forest. Because I really want to make sure that you're comfortable with these notions. Some live coding, working in the same skeleton code that we've given you for the final problem set, 3B. A little more theory, if you will, or methodology on parser evaluation, how to actually measure success. And finally, a quiz. So I hope we'll get through all of that, but I think the quiz will sort of keep us honest because we want to make sure we get through that. At least I want to. So let me briefly announce we've now officially decided, Erik and I, over coffee just before I came here, that we'll move the final lecture 1 week forward or back in time, depending on how you look at it. It will be on so 2 weeks from now. It's going to be the 25th of November. That means that this coming week you actually have your undivided attention to finish the final problem set that we've given you. We will possibly already tonight post last year's exam. Very soon we will. Well, actually, no, let me ask. So Erik and I discussed that choice. So some years we have actually not posted the sample exam before the session where we went through it. So the last exam preparatory session will be about 20 minutes putting things into perspective, wrapping up, and then most of that time will go to essentially answering your questions and making sure you feel comfortable about the upcoming exam. And we'll use last year's exam as a model, as an example exam. And so some years we've said, well, let's simulate an exam situation. You don't get to look at those questions beforehand. We just give them to you in that session. And then you need to make sense of them. But I think last year when I asked, not everyone thought that was the most effective way of approaching that session. So who would prefer that we not make available beforehand the sample exam that will be the basis for our final session? We will make it available afterwards, so you'll have all the time you want to look at it before the actual exam. So who would prefer that? The sort of play exam situation for 1 hour in our final joint session 2 weeks from now? And who would strongly prefer to actually have the time to look over that exam beforehand? Okay, that's what I suggested would be the case. So we'll post that exam, and I'll stop asking that question in future years, I think. You have stable preferences. And then that will be our final session 2 weeks from now. We'll update the course page accordingly. All right, so this is what we covered last time. Today we'll actually, in live coding, implement this notion of exhaustive unpacking. So Viterbi tree decoding, you might say, is selective unpacking. From the forest, just take out one tree that has the highest probability. Exhaustive unpacking means enumerate all trees. Solve that potentially exponential problem. We'll briefly go over Viterbi decoding one more time, fill in the missing pieces on parser evaluation, and have a quiz to wrap up. And I have prepared, I think, 4 of the slides from last week, and because I feel there's some conceptual depth here, I thought it might be worthwhile to fairly briefly mention the key notions one more time. I see some people nod. It's legitimate to shake your head. So, chart parsing as a general framework to compute all possible assignments of categories and all possible substructures. Filling in a chart with edges. Each edge accounting for a substring. It has a string start and end position where we count the vertices, the spaces between the words. And to generalize from the CKY algorithm, we had observed many of its limitations. A restricted class of context-free grammars, Chomsky normal form grammars, a rigid order of computation. We introduced this notion of partial rule instantiations, the dot here, somewhere in between the symbols beta 1 to beta n on the right-hand side. And that gives us a distinction between passive edges, fully instantiated rules, where the dot is at the end of the right-hand side, and active edges, or complete and incomplete items, where we found part of the right-hand side and we're still looking for some more. So these are intermediate states of computation. And this technique allows us to now go back to unrestricted context-free grammars, where we can have any number of things on the right-hand side, certainly more than 2, or also just 1, because for each intermediate step of computation we'll introduce an active edge. We effectively binarize the rule instantiation. We find one right-hand side symbol at a time. And that means that we could generalize or formalize the parsing problem in terms of this, you might say, deduction rule, where a suitable one active edge and one passive edge that are adjacent. The passive edge is to the right of the active edge. Its start index j is the end index j of the active edge. And its left-hand side category, beta I, is what the active edge is looking for. These can combine and give rise to a new edge. And that's the basic and only rule of combination. So that's, well, I consider that elegant, an elegant formalization of the chart parsing problem for unrestricted context-free grammars. That's an important thing to take home. And then we looked at how do we deal with local ambiguity in the chart, also in terms of the implementation aspects, because these are relevant to what you're currently coding. The general idea is to have only one edge for each category assignment alpha for substring I to j. That was the initial key insight we introduced for boys with hats from France. And to nevertheless record the different, the structurally different derivations that can give rise to alpha for this substring, the different subtrees, as sets of daughter sequence, of backpointer sequences in the representative edge. So an edge now represents multiple trees. And technically, identity of alpha I and j means that edges fall into an equivalence class, and that as we have computed a new edge E, the first thing we do is we search the chart for an existing equivalent edge, say H, and when we find such an edge, then we have detected local ambiguity. We found another structure that gives rise to the same category assignment alpha for substring I to j. And then we pack. And packing means that E is now stuffed, tucked away inside of H. It doesn't technically enter the chart. It sort of gets hidden away or put aside inside an edge that is in the chart already. And that means we'll not process E any further, because we know already that H is there and represents the category possibility for this substring. But packing E inside of H means we still have access to the daughter sequence, the backpointers, that actually led to E. So H now represents more than one tree. And unpacking then, we call the procedure of enumerating from this forest actual trees where each node is an unambiguous subtree, not a set of trees. So a packed edge is a set of trees. All right, and then we looked at this hypothetical parse forest and asked which of these edges are packed and which are in the chart, 2 is in the chart because it has become the daughter of another edge. 4 is packed inside of 2. So in each equivalence class, each oval, there can only be one representative edge that is in the chart, that has undergone further processing, that has had the possibility of becoming part of a larger tree, but each of them can have equivalent edges, well, packed into them. And then we asked for this hypothetical forest, how many complete trees are there? The answer is 9. And I asked you to sort of work that out at home, did you? We're good. Did you? Sure, many of you did. I would encourage you just one more time. And the technique is relatively simple. We can count effectively bottom up for the smallest subtrees or sets of trees. We can determine the cardinality of trees represented by each equivalence class. And then we sort of multiply as we put these subtrees as daughters into larger trees. So for example, this equivalence class represents how many trees? 2. Then this equivalence class represents how many trees? 2 for 6 and 1 for 7, 3. 2 trees here. Now we have 2 times 3, 6 for 4, and 1 times 3 for 2. That's 3. 6 plus 3, that's actually 9. So this node represents represents a set of 9 complete trees, and there's no more multiplication here, so 9 is the ultimate answer. Okay, so that was inside the parse forest. And that completes my recap in 10 minutes of everything we covered in about an hour, a little more last time. Any questions in this space? This one? The edges. Yes, so I've taken out the alternate view where I've bold-faced those that actually are in the chart and then shown what it conceptually means to have a daughter with a packed edge. That conceptually means that the entire equivalence class goes into that daughter slot. Well, actually, we have that here. So this is the alternate view. Here, the sort of daughter edges go to the entire equivalence class. But this is what we actually implement. So H is in the chart, E is packed inside of H. Yes? Alrighty, then I'll try an experiment in live coding. One of the few aspects in which Erik and I don't fully agree. He doesn't like live coding. I'll maybe ask you afterwards whether you do. But let me actually take a break, you guys at home. Wish you could have been here. Okay, let's come back. Welcome back. Let's move on. So that was half an hour or so on live coding. Was it worth it? Useful? Who thought this was a waste of time? Or too much time, let's say. Should have been faster. Okay, now I guess I'll just click through these one more time as I did last week. It's a tangent, sort of using probabilistic approximations of what actually is the intended structure meaning is not without controversy. So some of these quotes seek to document the breadth of opinions you can have about the utility of statistical or probabilistic modeling. Epstein actually is a game theoretician, so it's not that he's fundamentally opposed to probability theory, but I think, wants to caution us and say needs to be used with care. Chomsky has long been, I think still today, is highly skeptical of probabilistic approaches to natural language modeling, but they are what currently works best in natural language processing. I think that's an undisputed observation about the current state of our field. Fredrik Jelinek actually didn't win many friends when he made that claim. He was the head of, he was a pioneer in probabilistic approaches to NLP, headed the NLP research group at IBM Yorktown Heights, the research center, and pioneered both speech recognition and statistical machine translation. So had sort of some grounds to go on. But in much later invited presentation, 2004, so I think he chose the title for the presentation. Many of my best friends are linguists. So it's not all black and white. All right, but it's a very powerful tool, probabilistic modeling, to solve practical problems, to yield usable approximations, if not perfect approximations. We need to be aware of that. So we had, at the end of last week's session, observed that it's a relatively simple adaptation of the Viterbi algorithm over labeled sequences to Viterbi extraction of the most probable tree from a forest. And the sort of key observation is that we don't have sequential structure, but we have this recursive embedding that we have just studied in exhaustive unpacking, that we've also seen in counting the actual number of trees. So in Viterbi decoding, we do the very same thing. We compute the for each equivalence class the maximum probability and the corresponding subtree in the set of trees represented by that equivalence class. And we do that for the smallest trees first. And then, so that's what we record in the Viterbi cache, which is just indexed by edges. And sort of in this recursive formulation here, the recursion goes over the elements of the right-hand side, the daughter edges, if you will. And then we just take the product for each of the daughter subtrees and multiply that with the probability of the rule that we're using to put those together. And then again, we maximize and also keep track of which specific combination of daughter subtrees, one of these fours is the one that maximizes that probability. It's a fairly straightforward adaptation, I think. And if you now relate that to what we just did in counting the trees in the forest and exhaustive unpacking, I think it should be pretty accessible. Now let's talk about the one missing piece. Since you're implementing a parser, we need to evaluate how good it performs. And there are various aspects we could consider. There are parsers that return something for all inputs. Our parser will be one such parser because it's very robust. It's probabilistic in nature. I expect you give it the, it will probably return a tree. Not quite sure about the, but it's going to be difficult to actually find strings for which it doesn't return a tree, trained on the complete pen tree bank. But parsers that are less robust may not return trees for ungrammatical inputs. You could debate whether that's a desirable property or not. In grammar checking, it is not. So the inverse of coverage is overgeneration. If we have some notion of ungrammatical inputs, manually constructed collection of ungrammatical sentences that the developers of the Open Office grammar checker have obtained, then we might want to know how many of these does the parser actually incorrectly consider a part of the language. That would be overgeneration. In this class, we do care about efficiency, time and memory use. And Besides these three, which are relatively intuitive, I would like to think, or very intuitive, we also need to somehow quantify the accuracy. How good are the trees that the Viterbi decoding using a probabilistic context-free grammar trained on the Penn tree bank actually suggests are the intended, the correct trees. And one straightforward measure would be to say the percentage of sentences for which the correct tree is actually the tree returned by the parser. So we train on sections, what is it, 0 to 21, I think, of the Penn tree bank. We reserve section 22 and section 23 for evaluation. So that's our gold standard, as we did before. We train the parser, then we run it on the remaining gold standard data that we did not use in training. And we can quantify whether the parser actually brings back to us the tree that is also annotated in the Penn tree bank. That will not be the case too often. This is a very harsh measure. So for a state-of-the-art PTB parser, that will be less than 30%. That the parser returns the exact tree annotated in the Penn tree bank. These trees are quite complex. There are many choices, down to where do you attach a comma in the tree. And hence, to get a more granular, a more fine-grained, if you will, metric on how good these trees are, there's a standard way of breaking them down into smaller units. So saying that a tree that has everything as it is annotated in the gold standard except for the level of attachment of the final period is worthless is very strict. So most of the syntactic structure in that tree is correct. But still the sentence accuracy metric will score it as 0. It's not the exact tree that is annotated in the gold standard. It receives a score of 0. So Parseval measures overlap of sub-constituents. So we're back to that basic notion. And originally it was proposed in an unlabeled form, but now it's so that it's not considering the constituent categories, just the bracketings. But nowadays it's most commonly applied in labeled form. So what does that mean? Here is a gold standard tree, a pretty big dog's house. And here is what our parser might return for that tree. Obviously, these are not the same trees. But both say this is an NP, and there are substructures here. Dog's house is a num. So there's common structure. These trees are similar, but they're not identical. We want to quantify how similar are they and get this granular fine-grained metric. So what we do is we break the tree down into constituent labels. Spans effectively alpha, I, and j from our edges in the chart. And then that gives us two sets of constituent labels, or labeled constituents. We can intersect those. So those in red are correct. They occur both in the system output and the gold standard. And with that, we can compute recall and precision. That is, we can say how many of the constituent labels proposed by the parser are correct. That's precision. And how many of the gold standard constituent labels did the parser actually return to us? That's recall. And we compute F1 just as we did in classification. So breaking the tree down into, you might say, its smallest units, category assignments for one substring gives us this application of precision and recall to parser evaluation. And that gives us a granular metric. And state-of-the-art parsers will typically be around 90 points F1 score on the Penn tree bank, even above 90 point F1. So it will be curious to see where your parser ticks in on that competition. One might say here we evaluate two things, because some of these constituent labels are actually parts of speech, the pre-terminals. And we might say, well, we've done that. We're done with part of speech tagging. So one might only consider those constituent labels that are actually syntactic. So exclude the pre-terminals, the parts of speech. And that would then be an adjusted recall precision and F1 score. Sometimes, in addition to these, so this is the dominant way of measuring statistical phrase structure parsing accuracy. Sometimes this is complemented with counting how many brackets actually cross. So if you were to sort of put brackets, pairs of opening and closing parentheses into the string, then there is actually one where the start point precedes the start point of the second and the end point precedes the end point. So these genuinely cross. They are. So this is one bracket, this is the other bracket. They partially overlap. It's not a proper embedding, it's an actual crossing. And at the time, Black et al. Thought that sort of this is a serious violation. That is a serious error if you don't get the nesting, the hierarchical nesting right. So sometimes Parseval labeled constituent precision and recall, F1, is paired with counting crossing brackets. But we only ask you about the labeled precision and recall F1. Okay, that was not rocket science. So, in conclusion, this wraps up our, unless there are questions on parser evaluation. What is the system in precision? How do you mean that? Oh, this is system. So gold is the number of, so that's the cardinality of this set. And system is the cardinality of this set. But now the coloring well, there should be three things in red, or the denominator should be 2. Is that what you're picking out? So num here should be red. And fp should be red. So the coloring is not right. But fp is not a part of speech. That's this node here. It's an actual phrase. And num should be red. It's not a part of speech. It's this node here. It's an actual phrase. So there are three constituent labels that are not parts of speech. The parts of speech will have a category that is a part of speech, and they'll have a length of 1. They are the pre-terminals in the tree. So thank you. I should correct the coloring here. And then do you agree that the denominator should be 3 here? So it's the cardinality of things that should be red in this set. Excuse me? A cardinality which is not true. Yes, you're right. Right. Thank you. So it's actually, I just had forgotten how to interpret it. It's what is not grayed out. And red is what is correct. Thank you. So it's all good. I just didn't tell you how to interpret it. All right. So at this point, we have solved the 3 tasks we set out to solve. We can now talk about the probability of strings. That's n-gram language modeling. We can talk about probabilities of labeled sequences. That's sequence labeling, or in application to natural language, part of speech tagging. And we have introduced syntactic structure for ambiguous languages, general framework to parse with arbitrary context-free grammars, and associate probabilities with these trees, estimate those from labeled training data, and extract the most likely syntactic analysis. So we have met our goals. I would like you to go home with a fuzzy, warm sense of accomplishment. But you might still worry about actually qualifying for the exam. And here is, again, an opportunity to create a little bit of a cushion in our point system. So the quiz today will provide you with up to 4 bonus points that you can use towards completion of obligatory exercise 3. But again, you can only use these to make up for points that you missed in an actual submission. So if you scored 8 on 3A and 4 on the quiz, you're not done. Will not accept that. I also don't expect that will happen, but let's see. We certainly want you to work on 3B. And does everyone have a post-it in front of them? So write down your first and last name and your account name. And then there will be 4 questions. Prefix each line with the question number, and the answers will be short. This is an exam preparatory activity, so any attempt at cheating will be sanctioned according to Norwegian standards. So please don't talk to your neighbor. Don't consult any materials. Close your books and laptops, and work by yourself. After the quiz, put the post-it in front of you. Don't touch it. I'll come collect, and I'll ask you to discuss your answers with your neighbors. Time permitting, we'll then go through my answers. I actually didn't prepare my answers, so I think I'll ask you to give your answers. And last time you said several of you said there was not enough time. So I guess I'll give you 2.5 minutes per question. And if you all look terribly busy, then I'll even give you another 30 seconds. But we need to wrap up in the next 20 minutes. Ready? So here's my first question. Assume the following toy grammar of English has 3 syntactic rules, and S goes to NP, NP goes to det N, determiner noun, and noun goes to noun noun. That's a rule we haven't seen before. And the is a determiner, and we have 4 nouns: kitchen, gold, towel, and rack. So it's a nominal grammar. There are no verbs, only nouns. And I'm asking, how many different syntactic analyses, if any, will this grammar assign to the following 2 strings: the kitchen towel rack and the kitchen gold towel rack? So are these grammatical? Are these part of the language defined by this grammar? And if so, how many different trees will our chart parser find for these 2 strings? Go. Yes. Ooh. Still counting? Some of you are still counting. More time? Many of you are done. I think we'll move ahead. My next question. About the CKY algorithm. So here's the grammar that we know. And in fact, the CKY parse table that we've seen before. And I'm asking for the cell at row 0, column 5, containing the category symbol S, which is what I sometimes call the target cell, which pair or pairs of source cells or input cells could be combined to put S here, and which rule or rules of the grammar did I use? Question clear? So how do I get to put S here is effectively the question. You write down at least one pair of cells in this format plus one rule, and possibly more than one if you feel there were several combinations that resulted in the category S up there. So I want at least one pair of two cells. So in this notation, row column plus the rule. And so if you think that there are more multiple pairs, I mean, we know there must be one because there's S here. But there could be more than one way of deriving S for this span. So I want all pairs of cells in this notation combined with the rule that matches elements from those source or input cells. Go. Don't show this again. Thanks. Some are still writing. I'll give you a few more seconds. Okay, time to move on. I have another question. A packed parse forest, hypothetical. Which question do you think I'm going to ask? Just one number. How many trees are represented in this forest? It's an integer between 1 and 42. That's the most helpful I can be. Let's move on. Final question on parser evaluation. 2 parse trees for the kitchen towel rack. And that could be a different grammar. Don't read too much into that. What are the Parseval precision and recall scores for this pair of trees? Where we assume this is the gold standard and this is the system output. Okay, please put your post-its away. I'll come collect. And while I collect, I would ask you to form groups of 2 or 3 with your neighbors or anyone who you would like to group with and discuss this first question. So. Voor in? Ja. Kan vi snakke sammen med de? Er det den jeg skal? Nei? Any more post-its for me to collect? Okay, shall we give the answer? And I actually used our parser to determine the answer. I modified our read grammar to be that grammar of what is called nominal compounds in English. Norwegian does that without spaces. And English does it, so Norwegian compounding and German compounding is morphological. Donau, Dampf, Schifffahrts, Kapitäns, Patent. You may have heard about these. And English does it in the syntax. And that means I get bracketing ambiguity. So a kitchen towel rack can mean 2 things. It can be a rack, say in the store, for kitchen towels. Or it can be a rack, say for bathroom towels, we don't know, that is in the kitchen. So it can be a towel rack in the kitchen, or it can be a rack for kitchen towels. So we would expect 2 different readings. And when I parse that sentence, I get an edge, so it means it's part of the language. When I unpack, I get 2 different trees. And they either bracket kitchen towel or and then rack, or towel rack and then kitchen. So kitchen either modifies towel or rack. Adding gold, that was the best I can come up with to make that reasonably accessible. So it can be the kind of gold that you use in the kitchen, or it could be towels in the color of gold, or it could be a rack made of gold. And this is 5. So 2, 5. If we were to add one more noun, so I'll have to say a rack for racks. I don't have more nouns. Anyone have an expectation? It's more. You could have said that. It's 14. So 2, 5, 14. It's a series we actually know. It's the Catalan series. Sorry? So this is the same exponential growth we saw with PP modifiers. It's the same problem, only sort of packaged inside of the noun phrase. So 2 and 5. In the interest of time, maybe we'll just give the answers and you continue discussion once I conclude. So, which cells, which pair of cells, of input cells, or pairs of input cells, allow me to put the S here? I have to obey the notion of adjacency. So, column index of first is row index of second, and I need a rule. So S, I have only one rule, so NP-VP, I need a pair of adjacent NP-VP cells. 0 to 1, 1 to 5, that's 1. So these two are actually adjacent. They account for Kim, and the VP is Adores Snow in Oslo from 1 to 5. So they have the same J. The end index of the first is the start index of the second. Are there others? No. The local ambiguity is here. It's inside of the VP already. So 0 to 1, 1 to 5, S goes to NP-VP. How many trees? I didn't count them. How many are there? It's a simplified version of the forest we know. So 2 times 2, that's 4 here. 1 times 2, that's 2 here. So 6 here. I would say 6. Yes? And finally, what are the right numbers? 1? So we may have to spell that out. So what we would do is break it down into spans. 0, 1, 2, 3, 4. So 0 for S, 0 for NP, and so on. I think I would actually maybe not write them all down. I would sort of walk through the tree in parallel. Sorry? That's up to you. Let's maybe not do that. It's going to be easier. So these are correct. We're not counting the leaves. This, or shall we count the leaves? Let's count the leaves. So 1, 2, 3 correct. Is this correct? Yes, this n is correct because it is 0 to 4n. This n is correct. But this n and this n is not correct because this is 2 to 4 and this is 1 to 3. So these two don't correspond. This n is correct. So we have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. We have the same denominator in both. And we have 7 that are correct. So precision and recall and F1 are 7 over 8. I believe. Yes?
Did we count the S?
Certainly. Why wouldn't we? So if you say, I'm not counting the pre-terminals, then we have 1, 2, 3, 4 in total. 3 of them correct. So 3 over 4 or 7 over 8. 1, 2, 3, 4, yes. And 1, 2, 3, these are correct. This one is not correct. This one is not present. So this one is missing in recall and this one is wrong in precision. All right. Thank you for today. Varied session.